Hello and welcome. I'm Dr. Anton Vinogradov, a recent graduate here from the University of Kentucky, and this is using combinatorial multi-arm bandits to dynamically update player models in an experience-managed environment. All right, so in interactive narratives, we want to be able to give the player some agency in what sorts of actions that they take, but we also want to make sure that the author's goals stay intact. And in these two competing objectives, they can be balanced using something called an experience manager. And experience management is the process by which an intelligent system observes the player's actions and in some interactive narrative environment makes use of those observations to influence the player's experience, sort of in brief. By forming a persistent model of the player, the experience manager can make longer term decisions about the what to do rather than just in response to the player's immediate actions. And player models aren't really exclusive to experience management, but in our context, a player model is formed by observing the actions taken by the player and extrapolating those to inform future decisions by the experience manager. As the game goes on, we take more and more observations of the player, and we expect that the model of the player will increase in its accuracy. When using a player model in this way, we're tending to make an assumption that the player's preferences are going to largely stay the same. They might drift about a little bit as the player explores what's possible in the game, but the longer we observe, the better the player model should become, right? Well, this assumption doesn't actually hold true. It has been shown that the player's preferences can change and that dynamic recomputation needs to be able to happen to facilitate this. In an experience-managed environment, this poses a potential problem. When the player suddenly shifts their preferences, the player model can only really predict based on their previous preferences. And thus the experience manager is making decisions based on that outdated player model. This in turn limits what's in the environment, and what's in the environment limits what sorts of observations that the experience manager can take. Past approaches haven't really taken into account and can't really solve this problem. For a more concrete example, let me run through something. Imagine a player playing a game with a preference for combat scenarios, a fighter on Bartle's taxonomy of player types. The experience manager observes this, that the player is interacting with the combat a lot, and forms a player model saying, this player likes to fight. Now the experience manager continues to serve fights to the player to engage in. But oh no, the player has had enough fights and wants to try something different. Maybe they've grown tired of repetition. Given enough time, maybe the player model can adapt. But in the immediate, the experience manager is going to continue to serve up fights to the player. With no other way to make progress, the player doesn't really have a choice in what to do next. They can only continue to do fights. And if the player continues to engage, then the experience manager will observe this and not really be able to adapt. It's gotten itself stuck in a corner without a good way out. Now, in our previous work, we've shown that we can detect that a player's preferences have shifted, and additionally, we've shown that we can recover the player's preferences and form a fresh player model. But this second process is a little bit limited. And in this work, we're going to show that the player preferences can be recovered significantly more quickly. And we also run a human subjects experiment to sort of show its validity. But before we go on to the methods, let me talk a little bit about the environment. So our environment is built in a text-based game engine called Inform 7. It consists of several different areas representing a medieval fantasy town, which the player can navigate with the cardinal directions, north, south, east, and west. Within these areas are entities that the player can interact with, and each entity has a primary means for the player to interact with it, what we call the entity's action type. On each turn, the player will either interact with an entity or go to a different room. Now, there's 5 of these action types. We have look, talk, touch, read, and eat. And each action that the player makes falls under one of these action types. There's technically also a 6th one, the move action type, but I don't consider this one that the player can prefer since it's kind of necessary for the game. These action types also correspond to how we model the player, with the player model being the probability that the player chooses to interact with an entity of a certain action type. A player that prefers to talk will generally choose to talk to NPCs over combat scenarios. Now, to simulate the effects of a previous experience managing, we've made some tweaks to this environment. Some actions are very prevalent in this environment, like the talk action type, which is the primary means of solving the goal that the player is quested with. Other actions are still present within the environment, as a quest with really only one way to resolve it may not be super feasible. These are the look and touch action types. These, since they're present within the environment, are considered environmental action types. Due to us simulating that the player did not previously engage with reading or eating, the simulated experience manager just has removed these from the environment. Thus, these are considered missing action types. These two different distinctions, this grouping of action types, are important for our analysis later. And finally, there are a number of artificial agents that we use instead of human players for the first part of this paper. These agents are faster and cheaper to iterate it with, and thus serve a good basis to develop these methods, and I'll go over them in brief. Two of these agents, the goal and exploration focused agents, are inspired by Bartle's taxonomy of player types, namely the achievers and the explorers. And each of these agents takes actions in accordance to their sort of internal preference distribution, with slight different ways of choosing which action to go with next. But on top of that, the exploration-focused agent tends to explore a little bit more. It'll randomly move to surrounding rooms. And the goal-focused agent will tend to also try to complete what the next step in the goal is. The novelty-focused agent works a little bit differently from both of these. Instead, it takes its internal preference distribution and it combines it with this metric of like recency of how of each entity that it can see, with things that it's interacted with recently being ones that it wants to interact with less often, and those are combined together to get which entity it wants to interact with next. So with this environment, we used it in our improved player model recovery system, which now takes advantage of combinatorial multi-arm bandits. And like in our past work, we make use of distractions to be able to do this. These are specially crafted game objects that are intended to test the player's preferences. And given this purpose, there are a couple of restrictions on how they can be designed. First and foremost, they should not be interfering with the author's goals at all. Next, they should also largely be only noticed by players that are already distracted, not ones that are well engaged. And finally, for the purposes of testing the player, they need a well-defined action type. And with this associated action types, we can use this distraction as an arm for a multi-arm bandit, where an arm pull consists of the player model recovery system, adding a distraction to the environment for the player to interact with. Now, a combinatorial multi-arm bandit differs from a standard one in that it allows for multiple arms to be pulled in the form of a super arm. For our purposes, we define this as simply adding more distractions to the environment in a single round. For the reward, we only give it a single arm, or we only reward a single arm within that super arm, because we can see exactly which distraction that the player interacts with. And lastly, we make use of the CUCB method, a combinatorial UCB algorithm, which chooses which arms to pull in the next round. Now, to test this system, we're largely concerned with two things: how quickly can the player model be recovered, and how close it is to the correct one. Since we don't really have a method of figuring out exactly when it is recovered, we're going to be running these for a fixed amount of time. And we're going to be comparing the calculated player model to the player agent's internal preferences using the Jensen-Shannon divergence, with a lower value being a closer match between the two models. Now, the computed player model is calculated as the frequency with which the player has interacted with each action type starting at the beginning of the preference shift. For the actual tests, we'll be making use of the three agents previously mentioned. the 20 preference shifts that are possible, starting from one to going to another of the 5 action types. And we'll be using CUCB with a couple of different parameters. Namely, we're going to do a super arm with 2 distractions, another super arm with 3 distractions, and a super arm again with 2 distractions, but with a special modification active. These will be considered, or these will be compared against our previous best, the Epsilon Greedy, and also a theoretical best baseline, which sort of takes advantage of what how dumb our artificial agents are. Specifically, it gives one of each action type, sort of breaking the rules, allowing us to spawn 5 rather than just 2 or 3. Now, this modification that I mentioned is called the replace with environment action. And when active and distractions are being added, we look at sort of the types of distractions that are being played. And if they overlap with the action types that are already available in the environment, we will replace that distraction with the player doing any of that action within that round. This means that if a talk action is planned on being played, when it's replaced with the environment action, any talk action the player takes will be considered a reward for the talk arm. We've also found that this has a slight benefit of reducing the number of distractions that are played per turn, with in the first 10 turns allowing it to go down to about 1.7 distractions on average. But this goes up back to around 2 afterwards, as CUCB gets more information and can make better decisions. Now, for the results, we will be focusing on what we have in our past work identified as the most realistic scenario, the one that can cause the most trouble and is most likely to pop up, which is the environment to missing action type scenario, where it goes from something that is available in the environment to something, or preferring something that is missing in the environment. So one of the first things to notice is that you can see here that the our best performing ones are all of the combinatorial UCB, with the 3 arms generally performing better than just 2 arms, which seems to suggest that yes, having just more arms is better. But importantly, the replace with environment action option, when that is activated, that actually performs just as well as if there were 3 arms. And all of these also outperform our previous best of Epsilon Greedy. Now, we couldn't make use of the replace with environment action previously with multi-arm bandits, since we're only playing a single arm. And if we are to replace the single arm with something that's available in the environment, that would leave the environment fully biased. But with it active, it allows us to sort of not ignore what's in the environment anymore, sort of taking it in and allowing it to contribute to the reward of the multi-arm bandit. So this seems to be a good success. We are performing very close to that theoretical best at this point. I'm not sure how much more it can be improved, but I think this is a good time to move on to a human study to see if this is also working within human subjects. Now, to completely verify that this works with humans would take a lot of resources, and we would have to come up with an entire experience manager, implement it into the game, get it into all the players to play all the way through it, hope that they shift their preferences in it, and hope that we catch it with our preference shift detection method. And then finally, actually recover the player model. And that's a little bit out of the scope of what our resources allow. Instead, we have chose to test this system sort of in isolation to begin with. And with this, we set up a human experiment to test the combinatorial multi-arm bandit player model recovery system and ask the human participants to simulate the preference shift themselves, just for expediency. Despite this, it's still a little bit to change. Namely, this means the entire environment has to change. While those 7 rooms were great for our agents and led them to be less stuck and be able to actually complete the goal, this does mean that the player can just wander the entire area and explore it in depth in the sort of 75 turns that we gave them. So instead, we have opted to expand this to 36 rooms in these sort of 3x3 or 4 3x3 areas, which are connected in the middle. We hope that this, along with the 2 quests, each which takes around 20 turns each to complete, will keep the player busy for the duration of the experiment, or at the very least before the preferences have shifted, or they're asked to shift their preferences. One of the bigger changes to the environment is the switching out of the action types. Now, the action types are very good for our previous agents because they're sort of inspired by what's possible to do in a text-based game. But that's not really representative of how humans play the game. So instead, we switch to these, which is a new set of action types, sort of inspired by Skyrim. Additionally, we had to change out all the distractions. Whereas before the majority of distractions were generated from templates, these aren't really suitable for human players. And the main thing learned here is that in addition to the actions needing to be closely associated to an action type, this action type needs to be communicated to the player effectively. For example, you see a diplomacy scroll of some sort, an important treaty sitting on a desk, all unattended. Is that a stealth action type distraction, or is that a diplomacy one? So if a player gets confused, we're not really making good observations of what the player wants to do. So this sort of ambiguity led us to say they have to be readable. We also modify what's considered a round for the combinatorial multi-armed bandit. Previously, a round was equal to a turn in the game, which is very suitable for the agents, since they don't really care about things popping in and out of existence as they go about and do their things, but humans would. So instead, I chose sort of a natural delimiting point on room change. You go walk through a doorway and you forget exactly what you were doing. This also means that the reward to the arm has to be a little bit different. So instead of a round equaling a turn, it's now equal to within a room, and thus any distraction that the player has interacted with in that room is considered rewarded for the combinatorial multi-armed bandit system, CUCB algorithm. We've also had a little bit of technical difficulties when adapting this to the web, which means some of the information could not be communicated between the web front end and the back end, so the replace with environment action option could not be activated. To actually run the experiment, we opted to make it roughly match those of the automated agents, but roughly with a reduced scope. We're only testing a single preference shift scenario, the environment to missing, and we've reduced the number of turns to 20 before a shift, 5 before the distractions get activated, and 50 more to finish it out, for a total of 75 turns. For the task, the human participant was instructed to prefer to do actions that align with diplomacy, as that's what our quests were centered about, before switching to preferring crafting. And they were given examples of what this looks like, and they were given reminders of the instructions, as you can see here in the sidebar, after they've begun the game. And we recruited 30 participants from Prolific, though one of these had to be dropped due to just generating completely unusable data. For the results, we didn't actually have the ability to look inside a player's brain and extract what their preferences are, even though we told them. So instead, we've chosen to graph against a preference that is primarily one of the 5 action types. As you can see, each of these have 5 lines. We're comparing against sort of a primarily diplomacy action type. And alongside with that, we've also decided to show what is the effect of starting at different points where we start measuring our calculated player model. And given this data, we can say that even if we start measuring at the incorrect time, eventually the metric against the correct thing, which in this case would be versus crafting, will win over. But even including a little bit of data from that time, whether it be I think 20 turns in this case, does have a big impact. Curiously, you also spot that there's a drop in versus crafting even before we technically allow the player to actually get crafting actions. And this is an artifact of how we've classified our actions. where if the player attempts to do a crafting action, even if it's invalid, we still sort of count that as a crafting action. So currently, this system seems to be ideal in how it is able to recover a player's preferences and form a new player model, especially with the replace with environment action option active. But our human evaluation only really shows this working in a somewhat limited scenario. For a future full evaluation of this system, we'll require that we integrate this with our previous work on detecting player preference shifts, and also adding in a more proper game and an experience manager on top of it. Thank you for coming to the talk.